All right, today we're going to talk about geometric sequences and series, and I went ahead and put the solutions to lesson 11.2 on this first page right here so you can check your answers. And with that, we'll get started with geometric sequences and series. When successive terms of a sequence always have a ratio of the same non-zero number, then that sequence is called geometric. Okay, this sounds very similar to when we did arithmetic. The difference between an arithmetic sequence and a geometric sequence is there is a common difference between terms in a, common difference in terms of a arithmetic sequence, and there is a common ratio between consecutive terms of a geometric sequence. It's called the common ratio, usually denoted with the letter R. So a geometric sequence is defined as follows. The first term is A, and A sub n is R times A sub n minus 1. So it's just some number times the number before it. Okay? The terms of a geometric sequence with the first term of A and a common ratio of R is A times R squared, A times R cubed, and so on. Notice that the first term has no R, the second term has one R, the third term has two R's, the fourth term has three R's, so it's always one less common ratio than there is the term. All right, so find the initial term and common ratio of this sequence here, 2, 6, 18, 54, 162. All right, so the first term, simple. A sub 1 is 2. Nobody should ever miss that. Done. There's my first term. Now, the common ratio, let's see, 2 times 3 is 6, so the common ratio is 3. 16 times 3 is 18. 18 times 3 is 54. 54 times 3 is 162. So you need to check them all to make sure that you really have a common ratio, and so R is 3. So that's my common ratio. All right, prove the following sequence is geometric. So we did this with arithmetic sequences where we took two consecutive terms at random and we subtracted them and we got the same number. We got a constant number. If you get a variable in there, then it's not arithmetic. Well, it's the same thing with geometric. Okay? So we're going to take a ratio instead. So what we're going to do to prove, and this says prove, okay? So we're going to take 2 to the negative n plus 1, and we're going to divide that by 2 to the negative n in this case. Okay, and we're going to show that that is a constant number. Okay, so the first thing that I would do, I would get rid of these negatives. I'd flip this thing over, make this 2 to the n over 2 to the n plus 1. So remember, there's a negative power in the numerator, it goes to the denominator. If there's a negative power in the denominator, it goes to the numerator. Okay, what does this mean right here? Well, this means 2 times 2 times 2 times dot 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 times 2 n times. And this is just going to be the same thing, 2 times 2 times 2 times dot 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 times 2 n times, but times one more because it's n plus 1. So if that's the case, all these are going to cancel out, and I'm going to be left with 1/2. So that tells me that that's a common ratio. It proves, that implies it is a geometric sequence. Which I need to write. The initial term then would be 2 to the negative 1, which would be 1/2. And we already figured out the common ratio is right there, so the common ratio is also 1/2. Now, it just came out lucky that those are the same thing. They don't have to be the same number. But they were in this case. Okay, I should label this a sub 1, by the way, too. right, prove the following sequence is geometric. So I'll tell you what, we just did one. You pause the video here, do this proof, and then jump back on here and you can compare it with mine. Okay? All right, so what we're going to do to prove that this is a geometric sequence is we're going to take 4 to the n plus 1 power, and we're going to divide that by 4 to the n power. And we want to make sure there's no variables in here when we do this. So this is 4 times 4 times 4 times dot 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 times 4, where this is n times. And then since it's n plus 1, we're going to go times 4, one extra time. And then this is just 4 times 4 times 4 times dot dot dot. Well, that's terrible. Dot 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 times 4. And this is n times, okay? And then all these are going to cancel out, and I'm left with 4. So since that's just a constant number, that's my common ratio, r. So since I have a common ratio, that implies it is geometric. And if I wanted to find my first term, I just plug 1 in there, and that would also be 4. And again, that was, like I said, it doesn't happen every time, but it did on this one. Okay, so find a formula for a geometric sequence. Suppose A is the first term of a geometric sequence with a common ratio of r not equal to 0. So the common ratio can be anything, it just can't be 0, because then you just get 0 all the time, and that's boring. Okay, so find a formula for the nth term of a sub n. All right, so the first term is a. The second term is going to be a times r. The third term is going to be a times r, which is ar squared. Fourth term is going to be a times r times r times r, which is ar cubed. And I can see a pattern here. All right, the pattern is this, dot, 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 a sub n is going to be a times r to the n minus 1 power. There is my formula. It's always one less common ratio because the first term doesn't have a ratio. It's just whatever the first term is. There's my formula. And here it is again. A sub n is a times r to the n minus 1, where r is not equal to 0. Okay, find the 12th term of the sequence. So if my formula is a sub n is a times r to the n minus 1 power, I need to know what my common ratio is here. And my common ratio is going to be 9 divided by 10, which is 0.9. And you can check all these. This one's obviously easy to see. But if I take 81 tenths and I divide that by 9 over 1, remember I invert and multiply. So that's going to be 81 tenths times 1 over 9. And that's going to cancel with that. And I get 9 tenths. Okay, so the ratio here is 9 tenths. The ratio here is 9 tenths. And I can do the same thing here. I can say 729 divided by 100. Divide that by 81 over 10. That's 729 over 100 times 10 over 81. I can cancel a 10. And I can cancel let's see, if I divide this by 81, that will be 1, and that will be 9. And so this ends up being 9 tenths again. So that's got a common ratio of 9 tenths. Okay, and my first term is 10, so I can go ahead and plug this in here. I want the 12th term, a sub 12, is going to be the first term, which is 10, times the common ratio, which is 0.9, to the 11th power. So I get out my handy-dandy TI-84 plus C Silver Edition graphic calculator, and I go 10 times 0.9 to the 11th power, and a sub 12 is approximately 3.138 105. Okay, the sum of n terms of a geometric sequence. So now what I'm going to do is I got a geometric sequence, I'm going to add them all up. And that formula is S sub n equals A times 1 minus r to the n over 1 minus r power. I'm sorry. Let me say it again. S sub n, the sum of the first n terms, is A times 1 minus r to the n over 1 minus r, where r is not equal to 0 or 1. That's my formula. It's on your formula sheet. Okay, so find the sum of the first n terms of the sequence. So it's not a bad idea to write down our formula every time we use it, because it helps us to remember it, first of all, and it tells us where everything goes. So there's our formula. And we're going to use the sequence 1/2 to the n power. So that is, find the sum of 1/2 plus 1/4 plus 1/8 plus dot 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 plus 1/2 to the n power. Okay, so this is an infinite sequence. I'm really not going to get an answer to this. I'm going to get an equation. So my first term is 1/2, so S sub n is going to be A times 1 minus the common ratio. Now what's the common ratio? Well, the common ratio is 1/2. It gets 1/2 each time. So 1/2 to the n over 1 minus 1/2. Now, this can be simplified because this is 1/2 on the bottom right here, and then this 1/2 will cancel that 1/2, and I will just get 1 minus 1/2 to the n power. There's my formula. Now I'm going to find the sum of 1/3 plus 1/9 plus 1/27 plus dot 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 plus 1/3 to the 15th power. Okay, this one, since it has an ending, I'm going to get an answer to it. Okay, so again, I like to write down my formula. S sub n is going to be A times 1 minus r to the n over 1 minus r. So my first term is 1/3. So we're going to be finding S sub 15. So that's going to be the first term times 1 minus r. Now r is 1/3, because 1/3 of 1/3 is 1/9, and 1/3 of 1/9 is 1/27. So this is 1/3 to the nth power. That's going to be the 15th power over 1 minus a third. Okay, so S sub 15 is going to be 1/3 times 1 minus 1/3 to the 15th power over 2/3. And let's see, I can invert this and multiply, so the 3's are going to cancel, and this is going to end up being 1/2 of 1 minus 1/3 to the 15th power. Okay, so I'm going to get out my calculator at this point. 0.5 here. Okay, so 0.5 times, open parentheses, 1 minus, open another parenthesis, 1 divided by 3, close the parenthesis, to the 15th power, and then close the second parenthesis. And I hit enter, and this comes out to be approximately 0.49999999652. So that tells me something about this. I can look at this and I can say, you know, we've talked about limits before. If I took this on to infinity and just kept finding 1/3 of the previous one and adding it up, this is going to reach 0.5. Is going to be the limit on that thing. It's never quite going to reach there, but it's going to be as close as I want to. Okay. Find the sum of a geometric series. So the infinite sum of the form a plus a times r plus a times r squared plus dot 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 plus a times r to the n minus 1 plus dot dot dot. So this is a series that goes on forever. And sometimes I can find the sum of those things. Okay? So it's got a first term of a common ratio of r. It's called an infinite geometric series and is denoted by this. This is the sum from k equals 1 to infinity of a times r to the k minus 1. If this finite sum s sub n approaches a number L as n goes to infinity, then we say that the infinite series converges. If it does not converge, it is called a divergent series. Okay, so we'll take a look at that here in a second. So if the absolute value of r is less than 1, then the sum of the infinite geometric series is equal to a over 1 minus r. This is a formula that you'll probably want to know. It's very simple to use, and it's on your formula sheet. So, find the sum of the geometric series 2 plus 4/3 plus 8/9 plus dot 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 forever. Okay, so remember our formula is going to be a over 1 minus r. Okay, from right there, a over 1 minus r. So, what's the first term? That's a, that's going to be 2. And r, we got to figure out what r is. So, let's see, we can take 4/3 and divide that by 2 over 1. So that's 4/3 times 1/2, which is 4/6, which is 2/3. So r is 2/3. So we'll go ahead and put 2/3 in here. Now 1 minus 2/3 is 1/3. And again, I'm going to invert and multiply, and that's 6. So if I found the sum of this to infinity, I would get 6. So that is a convergent series, and it has a limit of 6. If we looked at one that, let's look at one that is divergent. So you see one of those. So let's say I had 2, 6, 18, 54, dot, dot, dot. Okay, so on this one, the first term is 2, and the common ratio is 3. So it'd be 1 minus 3 here. Okay, so what happens with this? Well, we can't even use the formula. It doesn't work because it violates this rule here. Okay, the absolute value of r is bigger than 1. So, because it's 3, right? Oops. So, since it's 3, if we start adding these up, these numbers just get bigger and bigger and bigger. And so this is going to go to infinity, okay, if I find the sum. So the sum, you know, the first 2 would be 8. It'd be 2, 8, 26, 80. And it's just going to keep getting bigger and bigger and bigger. So it's not going to have, it's divergent. All right, let's look at this. Prove that the repeating decimal, 0.999 to infinity, equals 1. There's several ways we can do this. Okay, we can use the sum of a geometric sequence, an infinite geometric sequence, because 0.999 repeating forever is 0.9 plus 0.09 plus 0.009 plus 0.0009 forever, right? So this is an initial term of 0.9. and then it has a ratio of 1/10. So if we use the formula a over 1 plus a over 1 minus r, minus r, temporary brain cramp there, then my first term would be 0.9, and my ratio would be 0.1. That's 1/10. And so this ends up being 0.9 over 0.9, which is 1. So we proved it. Now you might think that that's some kind of weird math magic, but it's not. You can actually prove it another way. You can do this. You could say, well, let's let x equal 0.9999 forever. And then that means that 10x equals 9.9999 forever. And now we could take, we could use some algebra. We could take this right here away from this. So I could subtract x, and I would subtract 0.9999 forever. And I would get 9x equals 9, and then I divide by 9, and I get x equals 1. So there's a second way that you can look at it. Here's another way you could look at it. You could say, 1 divided by 9, that's 0.111 repeating forever. 2 divided by 9, 0.222 repeating forever. 3 divided by 9, that's 1/3, which is 0.333 repeating forever. Notice the pattern here? 8/9 would be 0.888 repeating forever, which means 9/9 would be 0.999 repeating forever. And hey, wait a minute, 9/9 is 1, so I proved it a third way. How exciting, huh? You don't have fun like this in social studies, I'll tell you that. Okay, so we proved that 0.999 equals 1. 3 times. And I used to have a fourth way of doing it. I can't remember what that is off the top of my head, so we're just going to skip that today. Okay, so this is going to be our last. This is going to be our last assignment of the semester here. We're going to do lesson 11.3, and there it is. And I believe there's no problem 25 on this. Oh yes, there is. I thought there was a numbering error on here somewhere. So if you find one, don't freak out about it. I think there's a problem missing. So anyway, have a great day, and I will see you next time.